All right, this is a video where we are going to learn the limit comparison test, which is another one of the more useful tests that we have when we're dealing with series in calculus. But to start, what I want you to do is, I think I have 8 series here. I want to know, do they converge or diverge? And then state the test that you are using and show appropriate work. For example, if you were using the ratio test, you would want to tell me what the ratio is. If you're using the p-series test, you would want to show me what the p-value is. So there are 3 tests that are going to come up here. I'll tell them ahead of time to you so that you are ready to use all of them. First one you might use is p-series. Next one, ratio test, like I just said. But there's also some nth term test pieces or ones in here. So go ahead, hit pause, and see if you can identify which of those apply to these and why and how. Here come your answers. I accidentally said ratio test earlier when I meant to say geometric series. So hopefully you picked that up because we haven't actually talked about the ratio test, but geometric series. So what happens with these? The first two, they're p series. Here, remember, if p is equal to 1 or if p is 1 or smaller, then it will diverge. And if it is bigger than 1, it'll converge. So here p is 2, which is bigger than 1, so it converges by p-series. Here, the root is a p-value of a half, so it diverges by p-series because a half is less than 1. These two, here this one, if I take a number and raise it to the 4th power and then add it and continue to do that out to infinity, then it's clearly going to go to infinity. This thing diverges by the nth term test, and what's the easiest way to say that? The limit as n goes to infinity of n to the 4th, well, it's not 0. It actually is infinity, right? Next one, this one, as I start to get really big with my n values, this thing approaches 1 over 1. So it's kind of like adding 1 plus 1 plus 1 plus 1 for forever. So the limit is not 0. It also diverges by the nth term test. This right here, these 3 are actually all geometric series. So this one's geometric series because the ratio is a 4th. For each additional n value, I'm going to multiply by 1 over 4 one more time. And 1 over 4 is between negative 1 and 1, so it converges. Here, a ratio of 1/5, so it converges by geometric series. Here, this one, it might be a little bit harder to see, but I could write this as 1 over 3 to the n. And I think you should see that with each additional value of n, I will multiply by 1/3 one more time. So this thing converges by geometric series again. Last one, n squared over n plus 3, has the same problem that these two do. The terms don't go to 0. So therefore, it's impossible for them to, or for this summation, this infinite summation, to go to 0. So hopefully you're getting the hang of these and you are ready for the limit comparison test. All right, so the limit comparison test So it's limit comparison test. We abbreviate it LCT. It's a way to say that one series, sigma to infinity of a sub n, acts like another series, sigma to infinity of b sub n, where we already know that b sub n either converges or diverges. So I'm going to spell that out a little bit more. So the infinite series sigma to infinity of a sub n is the series that we're looking at, and then the sigma b sub n to infinity is the series that we already know about. Now, what the limit comparison tells us to do, it tells us to calculate L, which is the limit as n goes to infinity of a sub n over b sub n. And then there's kind of 2 cases. First, if L is any number other than 0 or infinity, and honestly, L is usually going to be 1, then sigma to infinity of A sub n and sigma to infinity of B sub n do the same thing. What do I mean by that? I mean they either both converge or they both diverge. So let me walk through it, and then we'll do an example, and I think it'll make a lot of sense. So basically, I've got one series, A sub n. I find a series, B sub n, that I know it usually does something. For example, I could take 1 over n cubed. And then I calculate this limit, L, which is the limit as n goes to infinity of the terms. So A sub n, there's no sigma. So of A sub n over B sub n. And if L is 0 or infinity, we kind of like don't go anywhere. That's our second case, right? But if L is any other number, anything other than 0 or infinity, then we know that A sub n and B sub n do the same thing. So let me show you an example. And it's going to relate. So here we have sigma from n equals 1 to infinity of n squared over n to the fourth minus 3. And the question is, does it converge or diverge? And what we're going to do is use the limit comparison test. So what I want you to notice is that I can take this thing and look at sort of, I guess we could call it the most significant piece in the top and the most significant piece in the bottom, and then get rid of everything else. So we're going to get rid of the 3, or the minus 3, right? So really what I can do is say, this is really kind of like n squared over n to the fourth. And then I can simplify that and say, all right, that's really like 1 over n squared. And what the limit comparison test does is it kind of says, well, because of what we just said, like when the 3 goes away, it kind of gives me this over this, which is that the limit comparison test sort of is a way to say that this acts like 1 over n squared. So what I'm going to do is this right here is my an, and this right here becomes my bn. So we know that sigma n equals 1 to infinity of 1 over n squared converges by p series with p equal to 2, which is greater than 1. We did that earlier up top. So what I'm going to try to do now is LCT it and show that this thing also converges by p series. So I will write it out. My an is equal to n squared over n to the fourth minus 3. My bn is equal to 1 over n squared, which I know what that infinite series does. So I then go and calculate L is the limit as n goes to infinity of an over bn. So that gives me n squared, whoops, didn't mean to move it there, over n to the fourth minus 3 all over 1 over n squared. Now you have to remember how to multiply by fractions, or deal with dividing by fractions, sorry. Some people like to say copy dot flip. Other people like to say multiply by the reciprocal. But this is equal to, or you could think about it if you want to see mathematically what's happening. If you multiply by n squared in the top and n squared in the bottom, it cancels on the top and stays in the top. Cancels on the bottom and stays on the top. But anyway, let's just copy dot flip it. You guys are probably like, come on, just copy dot flip it. This is the limit as n goes to infinity of, all right, the n squared over n to the fourth minus 3 times n squared over 1. So what I want you to see here, man, what's going on? So what I want you to see here is that I've got n squared times n squared. What's that? It's n to the fourth. So this gives me an n to the fourth in the top versus what's in the bottom, n to the fourth. You can use rules and ideas from pre-calculus to say, well, we just divide the coefficients. I divide the coefficient of this thing by the coefficient of this thing. What's the coefficient here? 1. What's the coefficient here? 1. I divide them, I get 1. So that means that L is equal to 1, which means that by LCT, by limit comparison test, this thing does the same thing as this thing. So what we say after this is that S sub infinity, and then remember, I'm going to come back up here and write S sub infinity there so that I know what I'm referring to. So S sub infinity also converges by LCT. Why does it converge instead of diverge? Well, that's because the p-series that we compared it to, that we used the limit comparison test with, it converged by p-series, right? So this one also converges by p-series. Let's try another one. So same question with this one. I want to know, does it converge or does it diverge? So the first choice we have to make is, it's limit comparison, right? Because that's what we're talking about here, and you'll learn how to recognize it eventually. But the first thing we have to ask is, what are we going to do a comparison with? Well, you're going to do the same kind of thing that I did right here. I got rid of everything except for the biggest pieces and then divided them. So here, what's the biggest piece? It is root, whoops, I'm trying to use this. It's root n. And what's the biggest piece in the bottom? N squared. So that would simplify to 1 over n to the 1.5 because the top's a half. So what I do is I say L is the, actually, before I do my L, I'm going to say that I'm going to do LCT with sigma n equals 1 to infinity of 1 over n to the 1.5. That's what I took over here, which, what does that do? Converges by p-series, comma, p equals 1.5 is greater than 1. So come down here. L equals the limit as n goes to infinity of root n over n squared plus 4, that's a sub n, divided by 1 over n to the 1.5, which that is going to simplify to limit as n goes to infinity of root n over n squared plus 4 times n to the 1.5 over 1. You can see that what is the total power of the top? Total power of the top is 2. Compare that with the 2 in the bottom. The limits, they will compete equally as n goes to infinity, and it gives me a limit value of 1. So, and I'll write S sub infinity equals S sub infinity converges, or also converges, by LCT. Okay, last example here. N equals 1 to infinity, n cubed over root n to the 7th plus 2n squared. Real quickly, see if you can figure out what we're going to compare it with. The same work as above. I just got rid of all the least significant pieces. I only kept the most significant pieces, the n cubed and the n to the 7th, simplified that to the 3.5, subtracted, and got n to the half. So we will LCT it with this, which diverges because of n to the half by p-series with p equal to half, which is less than or equal to 1. The LCT work will pop up in one moment. All right, so I divided the two terms. I moved the half up to the top. This is a 3.5. This is the only term that matters. It's to the 7th, but it's square rooted, so it acts like a 3.5, which gives me a limit of 1.
So S of infinity also diverges by LCT.